So today we will discuss about processors and controllers. So basically there are two things. One is processor and another is controller. And before coming to this, what is processor and what is controller? Now we have to go back. See, in 1945, first digital processor was produced, was made. Basically, what is there inside a processor? If we see that, then inside a processor, or in another word, we can say inside one CPU, central processing unit, we have registers. Registers are used to store content, store the data. And apart from these registers, we have ALU, that is arithmetic and logical unit, which is used to perform the operations, arithmetic operations and logical operations. And apart from this, we are having control unit. Now, the purpose of control unit is it generates various type of signal which is used to perform the operation of this CPU. Now, so this is basically our CPU, and this CPU must have a capability to communicate with memory. So here we have memory, and this CPU must be able to communicate with the memory, means content from the memory should reach to the CPU, then CPU will perform certain operation. The result, what is generated there, can be stored inside the CPU, or it can again send back and it can be stored in the memory, and at the same time, whatever result is generated, it can also be sent to output device. So here we are having this output device, and here we have one input device. So this is whole computer. So what happened in 1945? First digital CPU was made, and the name of that CPU was ENIAC. So this was the first digital central processing unit. So what is the meaning of digital central processing unit? This means this central processing unit was capable of performing the operation over digital data, right? So now, for the production of this CPU, the basic components which were used were, so vacuum tubes were used for the manufacturing of this digital central processing unit. Now, when vacuum tubes are used, then there is a problem with the vacuum tubes. When we are using vacuum tubes, then during the operation, it produces lot of amount of the heat, right? Now, due to that heat, there is a chances of there will be failure of the vacuum tubes. So, what happened during the operation of this digital processor, which was having vacuum tubes, on an average, after every 20 minutes, one vacuum tube got failed. Now you have to call the engineer, he has to rectify that problem. Again, you have to start the operation. Again, after 20 minutes of the operation, again some other vacuum tubes will fail. So that was the problem. Now what happened in 1949, first semiconductor device was invented, right? Like PN junction diode and PN transistor. So that type of device was invented in 1949. Now, all the vacuum tubes of the central processing unit were replaced by the semiconductor devices. So now what happened? The size of the CPU was reduced because the size of semiconductor device is very small as compared to vacuum tubes. And the speed of the operation increased, and the power, the heat generated was also reduced. So those central processing unit in which vacuum tubes were used, those CPU were come in the category of generation 1. Now, Now those central processing unit in which we have replaced the vacuum tubes, and we have replaced the vacuum tubes with the semiconductor devices. So those central processing units were in the category of generation 2, right? So now in generation 2, these generation 2 computers, they came in the market in mid 50s. So in 1955, IC, that is integrated circuit, that were developed, and these development of the IC was possible only due to the advancement of the technology. So now in integrated circuits, many semiconductor devices are fabricated inside single ICs. So now here the individual semiconductor devices of the central processing unit were replaced by integrated circuit. So now those central processing unit which were having integrated circuit as a basic component were come in the category of generation 2 computers, right? Now what happened? Now technology continuously advanced. Now in 1971, whole logic of the central processing unit was fabricated inside single integrated circuit, right? So the whole logic of the central processing unit was fabricated inside single integrated circuit with the help of large scale integration technology. Then that central processing unit was called as MUP, microprocessor. Mu indicates micro and P indicates processor. So that central processing unit, which we have fully integrated inside one single IC, was called as microprocessor. And that computer which was using this microprocessor as its central processing unit comes in the category of generation 4 computer, right? So what is the meaning of microprocessor? Microprocessor means when the whole central processing unit is fabricated inside single integrated circuit, then that central processing unit is called as microprocessor. So here we have this central processing unit. Inside this central processing unit, we are having registers which are used to store your content, your data, which is having ALU, arithmetic and logical unit, which is used to perform arithmetic and logical operation, and there is a control unit. When whole of this central processing unit is fabricated over a single integrated circuit, then this CPU called as MUP, microprocessor, right? And this microprocessor require memory where we will store our program or where we can store our data. It should be able to communicate with input device. It should be able to communicate with the output device. So now here, now there are two things, processor and controller. What is the difference between processor and controller? So basically, when we use processor, then in that case, this memory is external, right? So where we will store our program, we have to store our program in memory, right? So that memory is not the part of the central processing unit. It is external, right? You have to connect externally. And apart from this, we are having some more components like timer and some other devices like interrupt controller. All those things are external to this processor, right? So in the processor, basically we are having only register, ALU, control unit in over one single integrated circuit, and remaining things like memory, which is the external part, interrupt controller, that is the external part, right? Now, if we talk about controller, then in a microcontroller, we have registers, just like this processor. We have ALU, just like this processor. We have control unit, just like this processor. And apart from this, we are having here memory. So memory which was external for microprocessor now is a part of the controller, right? So memory, which is the external to this microprocessor, is now internal part of this microcontroller. And here basically there are two types of memory which are required. One is program memory. It is also called as code memory. So here we have to store our program in program memory or code memory only. And this memory is basically ROM, read-only memory. And the second part of this, second thing of this memory is data memory. So in data memory, we will store our values, our data, right? For example, if we want to sense the temperature of this room, then whatever current temperature of this room, we will sense this with the help of one sensor, and that value will be stored in the memory, and that will be stored in data memory, right? Because that is our data. Over that data, some operation will be performed by the controller with the help of our program code, which is in code memory, right? So now, apart from these things, there is timer, which is a part of the microcontroller. The purpose of timer is, in some application, we want to generate delay, right? So those delays will be generated with the help of timer. Whereas in case of the microprocessor, that timer, if we require, that is the external part. So externally you have to connect here timer. That is the external part of the microprocessor, but timer is the internal part of the microcontroller. Another thing, interrupt logic, right? So interrupt logic is the part of microcontroller. Whereas in case of the microprocessor, there is a special chip that is called as interrupt controller IC. A259. So that IC is external to this processor. If we require that, then we have to connect externally. Whereas the interrupt logic is the part of microcontroller. So these are few differences between microprocessor and microcontroller. So first microcontroller was manufactured by Intel company in 1981, right? And the part number of that microcontroller was MCS 51, right? That is microcontroller system 51 was the part number. So that microcontroller, the first microcontroller, was produced by Intel company in 1981. Later on, what happened? Intel company, they allowed other companies also to manufacture a microcontroller based on the architecture of MCS 51, right? And they allowed that, okay, so for example, there is company X. Now company X can manufacture a microcontroller based on the basic architecture of this microcontroller of Intel company, with some slight variation, right? With some slight variation. Slight variation means, suppose this controller is having a program memory of size 4 KB, then this company can have a program memory of size 16 KB. So this is a variation. So program memory size is more here. Now another company Y can also manufacture a processor, a controller based on this architecture with an internal program memory of 32 KB, right? Maybe third company, Z, can have 3 timers. Maybe another company, P, can have 64 KB program memory. So these variations Intel company allowed to other companies, right? So all those microcontrollers which were manufactured by these different companies and whose basic architecture was same, comes in the category of 8051 family microcontrollers. We will discuss what are the various things inside this microcontroller, right? For example, in 8051 microcontroller, I will write microcontroller with mu C, microcontroller. 8052 microcontroller. So we will see the basic difference between these two microcontrollers, and both of these microcontrollers comes in the family of 8051 microcontroller. Now here, what is the size of RAM, right? In case of 8051 microcontroller, the size of RAM is 128 bytes. In case of 8052 microcontroller, the size of RAM is 256 bytes. This means only 256 bytes we can store in RAM in case of 8052. Only 128 bytes we can store in case of 8051 microcontroller. And this RAM is the internal part of the microcontroller. Now come to ROM or code memory. So code memory, as I discussed that code memory is the memory where we will store our program code, So the size of ROM in case of 8051 microcontroller is 4 KB. And the size of ROM in case of 8052 microcontroller, it is 8 KB, right? So this is regarding the memory of this microcontroller. So now if we talk about 8051 microcontroller and about the RAM of 8051 microcontroller, then I will draw the basic internal architecture of this RAM, right? So this is the internal RAM, right? This is the RAM of 8051 microcontroller. So as I told you, total 128 bytes can be stored in this RAM. So always remember, at one location, we can store 8 bits only, right? Suppose this is location number 0, because all the 128 locations of this RAM will have some definite distinct address, right? Suppose this is location number 0, this is location number 1, this is location number 2, like this. In the last, it is location number 127. So we start from 0, the last is 127. So in total there are 128 locations, right? And at each location, as I told you, at each location we can store only 8 bits. So at location number 0 we can store 8 bits. right? Bit number, we will write bit number B0, B1, B2, B3, B4, B5, B6, B7. So from bit number 0 to bit number 7, these 8 bits you can store at location number 0, right? So as we know that 8 bits is equal to 1 byte. So at first location you can store 1 byte. At second location you can store another 1 byte. So total 2 bytes. So in this way, how many locations are there? 128 locations. At each location, how many bytes we can store? 1 byte at each location. So total how many bytes we can store? 128 bytes. So from location number 0 to location number 127, we can store 128 bytes, right? This RAM, which are here 128 byte locations. So basically, these locations are divided in banks, right? So there are in this RAM there are 4 banks. 4 banks, right? Bank number 0, bank number 1, bank number 2, and bank number 3, right? And each bank can have 8 memory locations, 8 registers. So this bank will have 8 locations. This 8 locations, this 8 locations, and this bank 8 locations. So in total, 8 plus 8 plus 8 plus 8, it is 32 locations. So total 32 locations are divided in 4 banks. These are bank 0, bank 1, bank 2, and bank 3, right? Right. So suppose here there are 8 locations of bank 0, right? So 8 locations means 8 register. As I told you, register is the place where we store our data, right? So this storing place, we name it as R0, register 0. Then next storing area, we name it as register 1. Then register 2. Like this, total 8 registers are there in this bank 0. So 8th register will be R7, right? So R0 to R7, these 8 registers are the part of bank 0. Then bank 1 will start. This is bank 1. Again in bank 1, we have 8 registers, right? So what are the name of those registers of bank 1? So name is same, right? Again, the first register of bank 1 will have name R0, then R1. In this way, the last register will have name R7, right? Then bank number 2 will start. The first register of bank number 2 will have same name again, R0, then R1. In this way, last one will be R7, right? This is our bank 2. And finally, there is bank 3. Again in the bank 3, registers are from R0 to R7, right? For bank 0, bank 1, bank 2, bank 3. Bank 0 has 8 registers from R0 to R7. Bank 1 has 8 registers from R0 to R7. Bank 2 has 8 registers from R0 to R7. Same way, bank 3 has 8 registers from R0 to R7. But now here, suppose I want to access. Suppose in my some instruction I have written register R0, right? I want to access the content of register R0. Now this R0 register is available in bank 0, it is available in bank 1, it is available in bank 2 and it is available in bank 3. Same name is available in all these banks. So, if we want to access the data from R0 register of bank 0, then how our controller will come to know that this R0 register belongs to bank 0, right? Or this R0 register belongs to bank 1, right? For example, I will write one instruction, move A, R0. Suppose this is one instruction, right? This is an instruction of microcontroller. The meaning of this instruction is the content of R0 will be moved in a register A, right? Register A is an accumulator, is a part of your microcontroller. Inside the microcontroller, there is a storing place named as A. And there is a register R0, right? If I have written this instruction, in this instruction, whatever is there in R0, that is a 8-bit data, that will be moved in A register. But the problem is, R0 is the part of bank 0, bank 1, bank 2 and bank 3. From where data will be moved? Data will be moved from this register, from this register, from this register, or from this register, right? So in that case, we must indicate this R0 belongs to indication. There is a register inside a microcontroller. That register is called as PSW, program status word. In program status word, this is a 8-bit register, 0, 1, 2, 3, 4, 5, 6, 7. These are the 8 bits of program status word register. In this register, bit number 3 and bit number 4, these two bits, these are designated as RB0 and RB1. Means register bank select bit number 0 and register. So in this program status word, there are two bits, bit number 3 and bit number 4. They are designated as register bank select bit number 0, register bank select bit number 1. So these two bits are used to select the banks, right? Now since there are 4 banks and these bits are RB1 and RB0, right? If these two bits are 0 and 0, then bank number 0 will be selected. If these bits are 0 and 1, then bank number 1 will be selected. If these bits are 1 and 0, then bank number 2 will be selected. And if these bits are 1 and 1, then bank number 3 will be selected. Right? And by default, the values of these bits are 0 and 0. Right? So if we will write this instruction, move A, R0. So in this instruction, if by default the value of RB1 and RB0 is 0, 0, then the content from R0 of bank 0 will be transferred to A register. So in this instruction, the content from this register, which is a 8-bit content, will be moved in A register. And if we want that content from R0 of bank number 1 should be transferred to A register, then we have to make RB0 1. If we will make RB0 1, then what will happen? 0 and 1. RB1 is 0, RB0 is 1. This position. So in this case, our bank number 1 will be selected. So the value from R0 of bank 1 will be transferred to A. Right? Now, how to make this bit 1? For this, there is an instruction. For example, set B. If you write this instruction, set B. Set B means set bit. Which particular bit? PSW dot 3. If you write this, bit number 3 of PSW will set by this instruction. So this bit will become 0. And after that, if you write this instruction, move A, R0, and content from R0 of bank number 1 will be transferred to A register. And if We have made this bit also 1. Then in this instruction, content of R0 from bank number 3. From here data will be to transfer to A. So in this way, we can access these registers of the bank. Now there is one more method to access these registers. You can access these registers with their address also, right? For example, R0 of bank number 0 is having an address 00H. R1 01H. Like this, the 7th register, R7 register will have the address 07H, right? So bank number 0, it will have the addresses, bank number 0, it will have the registers R0 to R7 and addresses will be 00H to 07H. Then bank number 1. In bank number 1, again we have R0 register and up to R7 register. Now here R0 register of bank 1, what will be its address? R7 register of bank 0 is having address 07. So R0 will be having next address of 07. Next number after 07 will be 08. So it will go up to 0FX. F means hexadecimal number. So this register R0 of bank 1 will have the address 08H and R7 will have the address 0FH. Right? Now the next register R0 of bank 2 will have the next address after 0F, and that will be after 0F, the number will be 10H, and R7 will have the address 17H, right? So bank 2 registers addresses will be from 10H to 17H. Now R0 register of bank 3 will have the next address after 17H. After 17H, the number is 18H, and the last register R7 will be 1F. These are the addresses. So we can access these registers by name or by address also, right? Same way, for example, in this instruction, in place of this, I can write this also. Move A, 00H. Now what will happen? Data from address 00H will be moved in A. What is the 00H address? 00H address is the address of R0 register. So in this case and in this second case, both the instructions are performing same operation, right? So this is about the register banks. So here we have X from address 00H to 1FX, and total registers here are 32 locations. Okay. So all the 4 banks are having total 32 locations, right? After these 4 banks, the next address is after 1FH, the next hexadecimal number address is 20H, right? From 20H to 2FH. These are 16 locations. And these 16 locations are bit address. Bit address. The meaning of bit address means you can access individual bits of these locations. For example, location number 20H. As I told you already, 8 bits you can store at this location. 1, 2, 3, 4, 5, 6, 7, 8. So here in this at 20H location, you are having 8 places where you can store the bits. And you can access the individual bit also of these 16 locations, right? So if you want to access this,
you can access this bit with the address 00H. This bit is having an address 01X. Like this bit is having an address 07X, right? So in this way, the last bit will have the address 7F, right? So in total, there are 16 locations. At each locations, we have 8 bits. So 16 into 8. How much it is? 128. So total there are from 00 to 7FH. There are 128 bits. So each 128 bits you can access individually. For example, if you write instruction set B 00H, what will happen? This particular bit of this address will set, right? So if you write the instruction set B 7FH, then what will happen? The bit whose address is 7FH will set. What is that? 7FH is the address of this bit. So out of 128 bits which are available here, this particular bit will become 1 with the help of this instruction, right? So total 32 locations are for bank, 8 locations are for bit addressable memory. So total how many are there? We have used, it is 8 and 4, 48 bytes. And total in 8051 microcontroller, we have 128 bytes, right? So you minus this, the remaining is 80 bytes, right? So those 80 bytes are called as scratch pad registers, right? Scratch pad registers, and they are from address 30H to 7FH. So this whole is the architecture of internal RAM of microcontroller 8051. Okay, now we will discuss about one application of the microcontroller. Suppose this is the microcontroller 8051. In this microcontroller, at pin number 1.0, we have connected one switch. Here it is plus 5 volt. Ground, and this is the switch. Name I have given S. This is push button type of switch I have connected here. Now basically what happens in the switch, even in the desktop computer switches, whatever we are having, there is push button type. There is a plastic cap. But inside the plastic cap, you will find there is a metal. Right? There is a metal. So if you press this switch, then this metal will come in contact of this metal line. This metal will come in contact of this metal line. When we press this switch of this laptop, so what will happen? There is a short circuit. Short circuit will take place. And when we release the switch, then again this metal which was earlier in contact with this metal line will come out. So now it is open circuit. So when we are not pressing the switch, at that time circuit is an open circuit mode. And when we press the switch, at that time it is short circuit. So now this pin, this switch is connected. This end of the switch I have connected to plus 5 volt through one resistance. The second end of this switch I have connected to ground. So right now, if this switch is an input switch, then if we have not pressed the switch, then at that particular point of time, if we read the value at this pin, you will find plus 5 volt. Right? You will find plus 5 volt. And when you press this switch, then this metal will come in contact with this metal. So it will look like plus 5 volt resistance. This is just short circuit and this is ground. This is switch S. This is pin number 1.0. So when we press the switch, then it looks like this. It is a short circuit. So now this point is connected to VCC through one resistance. This point is connected to ground through this short circuit path. So what will happen? Resistance, this short circuit path will have very low resistance, around 10 ohm. Here resistance is high. So what will happen? This pin will be connected to the ground through the short circuit path, and you will read here a value 0, ground, right? And when we release this switch, at that time this is open circuit path, right? Under this position, this point is connected to VCC through this resistance, and this point is connected to this ground through this open circuit. Open circuit means very high resistance in the range of megaohm. So in that case, this point, if we read the value here, voltage here, then we find the voltage plus 5 volt, that is binary 1 at this time, when we have not pressed the switch, right? So we have to read this condition, when we have pressed the switch and when we have released the switch, and depending upon that, I have connected here one LED. One LED is connected at pin number 3.0. Right? So my aim here, if S is not pressed, right, on LED will glow, and if switch S is pressed, then off LED should off, right? So whenever you press the switch, then this LED should off, and whenever we release this switch is not pressed, LED should on. We have to perform this operation, right? To perform this operation, we have to write a program in assembly language, right? So here we will write a program. ORG 0000, right? So here, this ORG means origin. This is a directive, right? This directive indicates the assembler that whatever you have written after ORG, that is the starting origin of our, that is the starting location of our program. So our program will be loaded at location 0000H of the code memory of the ROM. Right? After that, now I will write the program. First, by default, all the pins of the microcontroller are the output pin, and you will get high value here. Right? If you want to make any pin ADU input, you have to send binary 1 to that pin. So here in this case, pin number 3.0 is the output pin because we have connected a LED, whereas pin number 1.0 is an input pin because we have connected a switch. We want to read the value of this switch. So this pin should be input pin. To make this pin input, first I will write an instruction set B P1.0. Right? So this instruction will it will make pin number 1.0 input. So now this pin is input pin. Now I will monitor the value of this pin. Right? Depending upon the value, whether this pin will be at binary 1 or this pin will be at binary 0. Only two values will be there. Depending upon these two values, I will make my LED on or LED off. Right? So for that, I will write one instruction JNB. JNB means jump no bit. Jump no bit P1.0. If pin number 1.0 is 0. JNB means jump no bit. If it is 0, then you jump to one particular place. So jump no bit. What is the meaning of jump no bit? If P 1.0 is 0. When it is 0? When we will press the switch. When we will press the switch, at that time you will get this 0 ground value at this. So when we will press the switch, this condition, number 2, if S is pressed, off LED. the program at location of LED. This is of LED, right? So here I will write the instruction to off my LED, and here now I will write the instruction to on my LED, right? So to on the LED, set B 3.0. Make this pin 1. This is LED, this is N, this is P region of the LED. N is already connected to ground. If you apply a high voltage here, then this LED will glow. That's why I have written set B 3.0. And here we have to make the LED off. How LED will be off? To make this pin 0. So CLR P 3.0. And here I will write another instruction as jump REP, repeat. We will repeat it this way. REP. Here as jump REP. Right? Now we will see with one example. Suppose we have pressed the switch. Right? Now what we have? If we have pressed the switch, value at pin number 1.0 will be 0. See this instruction jump to no bit P1.0. If P1.0 is 0, then go to off LED. So in this case, program will go to this level, right? And here the first instruction is CLR P3.0. So now with this 3.0, it will become 0. If it will become 0, then this is 0. And terminal is connected to ground. Both P and N terminal at the same potential. That's why this LED is off. That is the condition that we require. When we press, LED is off. Once the LED is off, S jump. This is short form instruction. S jump REP. Repeat. Go to the label repeat. This is the repeat. Again check what is the value of this switch. So in this way, once you write this program, then continuously whenever you will press the switch, LED will become off. And if you will release the switch, then LED will be off. Right? This is the application of one program. So in this subject, basically for the examination point of view, what you have to do for 8051 microcontroller, you just study the architecture of the controller, differences between processor and microcontroller. Now in the architecture, you study about the architecture of the RAM, various special function registers like program status word register. In program status word register, there are various flags, right? Like overflow flag, carry flag, auxiliary carry flag, right? So when some addition operation or any operation is performed by the microcontroller, then after the operation, whatever result is generated, depending upon the result, what will be the various values of program status word flags that you have to study. Then after that, you should study addressing modes, right? For example, direct addressing mode, register indirect addressing mode, register addressing mode, immediate addressing mode. These addressing modes you should study. And also you must have the knowledge about what are the valid instructions, what are the invalid instructions, right? For example, if I write this instruction, move R0, R1. So content of one register, you want to move in another register R0. So whether the instruction is valid or not, that also you must have the information regarding this. Then you must study about the instructions, right? Then regarding timers, regarding the application of the timer. For example, if you want to generate a delay of 10 seconds, then how to write a program. If there is a traffic light control There is a traffic light control operation logic is there. Suppose one red light is on for 20 seconds. After that, red light is on and yellow will also on for 5 seconds. After that, red and yellow both will off and green light will off for 20 seconds. If that type of logic, how to write a program for that? Suppose you want to generate a square wave of 10 kilohertz, then how to write a program? So for this, you require timers. Then you must study about the interrupts. What are the various vector rotation of the interrupts? How to write a program with the help of interrupt, right? So in this, you have to study a register, i.e. interrupt enable register, IP register, where you can fix you can change the priority of the interrupts. For the timers, you have to study keyboard register. You should study icon register, right? So these are registers. Then you should study serial communication. Right? How to transfer data serially. So in that, when we are transmitting a data serially, whether we are receiving a data or we are transmitting a data, then at that time we have to transmit or receive the data with particular baud rate. Right? For example, 9600 baud, you have to transmit the data. So for that transmission, what should be the value, what should be the control value that we have to load in the timer register, right? So that 9600 baud operation should be done, right? Transmission or reception of the data at 9600 baud should be done. For that, you have to load some control value in timer 1. So what should be that value? So you have to study that also. Then for the interfacing, you have to study how a keyboard is interfaced with the microcontroller, right? Keyboard interface. Then a stepper motor. How to interface a stepper motor? Then LCD interfacing. How to interface LCD, right? And how to interface 7-segment display. Right? If you want to display numbers from 0 to 9, right? How to write a program, how to interface the 7-segment display for that, right? Then ADC, analog to digital converter. Then DAC, digital to analog converter. How to, what are the basic pins of these devices, and how to write the program for DAC to generate a triangular wave, to generate sawtooth wave, to generate a square wave. These type of small programs also you can study. Now, this is about microcontroller. Now, in case of microprocessor, we have to study 8086 microprocessor. In this, first you study the architecture. In architecture, basically you have to study the first interface you need, VIU and EU, execution unit. So, if this architecture is having VIU and EU which are operating in parallel, then in that case, what are the advantages and what are the disadvantages? There is basically no disadvantage, all advantages are there. So, what is the advantage if we are having VIU and EU operating in parallel? So, first advantage is we are having pipeline feature. So, you study about the pipeline. Okay? What is the advantage of the pipeline? How pipeline is implemented? Okay? Now, in this, you have to study physical address. How to calculate the physical address, right? How to calculate the physical address under different addressing modes. So that you have to study. And when you are studying the physical address under different addressing mode, then naturally you have to study about the various addressing modes. And again, you have to study here various instructions, right? Then you have to study about the interrupt. So 8086, there are 256 interrupt. type 0 to type 256 software interrupts are there. So if for type 0 interrupt, what is the vector location for type 0 interrupt? For type 2 interrupt, what is the vector location for type 2 interrupt? And then how to calculate these memory locations, vector location. You must know this. Then what is the advantage of memory segmentation? So memory segmentation is an important feature of 8286 microprocessor. So what is the advantage of that memory segmentation? That you have to study. Then you have to study about instructions only. You have to study the instructions, then programs. Yes. Programs, some basic programs. You can study like to clear your doubts of various instructions. You can study about how to arrange the number in ascending order, how to arrange the number in descending order, to find the largest number from a series of many numbers, smallest number, and suppose there are few bytes stored at one memory location, how to transfer these bytes to some other memory location, and some other programs also. You have to study those type of programs. So in this way you can cover this CO also. And apart from this, you study about PIC microcontroller. So in PIC microcontroller, basically you study about the architecture of the PIC, what is the data memory map of the PIC, status registers of the PIC, what are the various flags of the PIC register, right? The timers of the PIC. So in this way you can cover this. Here 8051 interfacing of various external devices will be there, and here there is basically no interfacing. Interfacing part is not there, but programming, calculation of physical address, instructions, pipeline, memory segmentation, all these things we cover, and we pick basic architecture and these type of things you have to cover. All the best for your examinations. Thank you.
For more updates, download the KL Radio app on Play Store or visit www.kluradio.com.